postdoc here with Professor Siddharth Burman. Previously, she completed a PhD at IIT Gandhinagar with Professor Neeldara Mishra, where she worked on topics in fair division, matching, and computational social choice. And today she's going to be giving us an introduction to fair division and computational social choice. Over to you.
Hello. Hi, am I audible to everyone? Okay, thank you Satya for the introduction, and I would like to thank the organizers first for managing all this stuff, and I hope you have had a great learning experience over the past couple of days. I understand that this is a post-lunch session, so if you guys will feel sleepy about it, but bear with me. I'll talk about cakes and how to divide them fairly, and I'll hopefully try to convince you that cutting a piece of cake is not really a piece of cake. And we'll see that researchers have spent like decades of their work researching on how to divide a cake fairly among interested kids. So metaphorically speaking, the cake here means a very valuable resource that is divisible, right? You can cut it down into fractions and give it among the interested agents who have preferences over different parts of the cake, right? What all I'm talking about comes under a big umbrella of what we call as computational social choice. What is computational social choice? So this is a theory of aggregating individual preferences into a collective decision. So you guys might have seen a lot of matchings, stable matchings, right? Over the past couple of days, where you have preferences of some agents that are captured by either rankings or cardinal utilities, and they want to be matched with their best possible available outcome, right? So this is one aspect of computational social choice. Then there are voting scenarios where people vote and elect a committee or elect a politician or whatever, and the aim is to aggregate all these voting into a fair judgment so that everyone who voted feels happy about it. Okay, I voted for the right person and the right candidate is chosen. So what are these kind of voting rules? That is another aspect of computational social choice. Today what we'll look at is one another aspect, which is called resource allocation. These resources, the underlying resources, are some valuable resources which could either be divisible or indivisible, and agents have preferences over them, and our goal is to kind of allocate all these resources completely among the interested agents. Okay, so this is the theory of social choice. We will see what properties a good decision, a good division should satisfy. Intuitively, we might want it to satisfy that everyone feels fair about it, that everyone feels that okay, I have received a deserving share of whatever was available. Also, not only this individual perspective, we'd also want to maximize the collective welfare on the society as a whole. So these are the two aspects that we'd be interested in. The first question arises is, does these good allocations always exist, or good decisions always exist, or good matchings always exist? This can be modeled across various scenarios. And once such decisions exist, if we have the existential guarantee, the next question is if we can find them efficiently, if we have protocols or algorithms or well-defined procedures that can lead us to those good decisions. Right, so this is the outline of the talk. We'll see how where this kind of framework is applicable. So to start with, I started with the metaphor of cake, which is a well-defined metaphor that is used widely in the literature. This cake kind of encompasses many scenarios. You could think of it as like border negotiations or land divisions that happens across international borders. You could think of it as division of rent among the flatmates. You could think of it as casual scenarios, as like dividing dinner bills among a group of friends, or dividing time slots in the scheduling of conferences, etc. Okay, so this is one aspect. Another aspect is of indivisibility, where you cannot kind of break the resource available. For example, if you are interested, if you look at the organ transplantation and stuff like that, so one entire organ has to go completely to one person. It cannot be shared, it cannot be divided. Same for vaccines, same for house allocations. If a house has to go, it has to go to one family, right? Then there are course allocations among students. Then there are inheritances and division of valuable resources and divorce settlements, and so on and so forth. So there are many applications where we want to allocate resources, divisible or indivisible, among the interested agents. and agents have preferences over them. That is the most complex part of it. How do we elicit these preferences? How do we take into account these preferences and then come up at an aggregate decision that is fair and welfare maximizing with respect to those preferences? So this is the main area that we'll talk about, and we'll see very simple algorithms both in divisible and indivisible setting. Okay, to begin with, we'll see a division of divisible items, and let me just motivate the model first. So we'll represent a cake by an interval, a 0, 1 continuous interval. There are some agents and they have some valuations. So we'll say that an agent value the entire cake at one number, say 1. So this is called normalization, that the entire cake has a value 1. And now if you look at fractions, every agent will assign some fractional values to different intervals of this 0 and 1. We'll assume that these valuation functions are additive. That is, if you take two subintervals, your valuations of the combined added union of these subintervals is just your individual valuations added up. So this is the additivity assumption. Okay, so now how do we input all these preferences into our fair division model, right? These are continuous intervals and it is complex to capture all these valuations. So what we resort to is a complexity model which is called query complexity. Here we have two kinds of queries. First is the evaluate query. So what you can do is you can give an interval x comma y, which is a subinterval of 0 and 1, and evaluate it for agent I. You can ask this oracle kind of a model, hey, what do you, for an agent I, what do you value this chunk x and y, right? So this oracle will then output you whatever the value yeah. So this eval query will output you the value that agent I has for the intervals x and y. Another query that would be of interest is this cut query, where we'll ask, okay, you start at a point x somewhere in this interval and a number alpha, output me a point y such that the value of x and y is equal to alpha, right? So these are the two kind of queries that we'll deal with, and the complexity of the problem will be to bound our decision in terms of the number of queries that we can ask the oracle. We cannot ask an unbounded number of queries, right? So we'll want to minimize the query complexity and then find some fair divisions of the cake.
So
Okay.
here xy is the interval,
Yes.
endpoint of the interval.
Endpoints of the interval. Okay. Yeah, so if you look in the figure here, eval query outputs the alpha, what is the value of this interval, and the cut query outputs the value y. Where should you cut the cake so as this agent I receives a value of alpha from the interval x and y. This is a very simple model, and it will be really interesting to see that how it can simulate many cake division algorithms with this simple setup. With this two kind of queries, we can kind of find fair divisions of the cake in many aspects. Okay. Okay, so I talked about fair divisions of cake, right? What do fairness mean in this context? So one share-based notion of fairness is proportionality, where every agent wants that he should get at least, if there are two agents, every agent would want that he should get at least half of the resource. If there are n agents, everyone would want that they get at least 1/nth of the resource, right? This is called proportionality. It was, and these are like well-defined concepts that has been studied from 1940s, 1950s. Next, envy-based notion is of envy freeness, where fine, you may have proportionality, you may not have proportionality, but what we want is when every agent look at what his fraction of cake that he has gotten, he should value it more than the other pieces, pieces that other agents have gotten in that allocation, right? So formally we say that vi of xi, which is the allocation of agent I, the fraction of cake that agent I got, he should value it more than he values any other piece that is allocated to some other agent. Are the definitions clear? They make sense? Okay, so let's see if we can design a simple protocol for guaranteeing an envy-free division for just 2 agents. So, are there any suggestions? How should we go about it? There are only 2 agents and there is one cake that is to be divided among them. And what we want is everyone should, nobody should envy the other person. Okay, so the 50-50 thing is based on preferences, right? I might not like the 50 share of the cake that I got. I might have preferred the vanilla part, which is now given to the other agent.
So the one person divides and the other person chooses.
Exactly. This is a very basic protocol that we do, and it has its bibliographical references. It was known in many manuscripts 2000 years dated back. And what you do is just one person cuts the interval into 2 parts that he thinks are of equal value to him. Right, so agent 1 is coming here and cutting the cake into 2 parts, and now he's fine. Whichever piece agent 2 will pick, he will be fine, right, because he has made an equal division of this cake, right? And then what happens is the second agent comes and he picks his favorite piece from the 2. Do you see that? Is there a possibility that agent 2 might envy agent 1? No, right, because he got the right to choose first. So he would have chosen, if he envied, then he would have chosen the piece x2, right? Okay, and agent 1 is also envy free, right, because he divided equally, so there is no point of envy from his perspective. Can you say that this division is also proportional? Okay, is it proportional for agent 1? He is getting half of his utility, and that is the definition of proportionality, right? If there are 2 agents, I should get half of it. The second agent, if he does not get half of it, let's say he gets 1/3 of the cake, then 2/3 of the cake, according to his preference value, goes to the first agent. Then he'll envy the first agent, right? So if he were to choose, then he would have chosen the 2/3 of the cake, right? So then it is also proportional, right? So, are there any questions?
Should they add up to 1? Like,
Not necessarily.
okay.
Not necessarily.
Then
So it might happen that agent 1 derives a value of, let's say, 0.7 from his bundle, and agent 2 derives a value of 0.6 from his bundle. The valuations are distinct, disjoint, may be conflicting.
No, not like that. Like the cake is given. Like I cut it at some point. If I look at agent 1's valuations over these 2.
Yeah, that should add up. That should add up to 1. That follows from the normalization assumption that the value that an agent I gives to the entire cake is 1. So if I divide it into 2 parts, that should add up to 1 for one agent. But when you are looking at the final allocation, we won't say that the value that each agent derives must add up to 1. It can, because the preferences can be conflicting. I could like different aspects of the cake, and it may happen that the allocation is so nice that agent 1 also derives a value of 1 and agent 2 also derives a value of 1. Right?
so the parts of the cake that one agent gets need not be a continuous interval, right?
Need not be a continuous interval. This is a very good question, and we'll see that if we insist on continuity, then we might not be able to compute such allocations. These allocations exist, we know for sure that you can find an envy-free contiguous chunk of divisions, but the computation part is not obvious. It is not known. But if you throw away this assumption of continuity, then there is a finite bounded protocol that will guarantee you envy-free division. So yeah.
Is the cake symmetric or asymmetric? Like if we cut from the starting and then say 10% of it, or from the end and that's the 10% of the cake. So are their values same or?
No. The cake is heterogeneous. It could have different values. It's not non-uniform. There is no assumption on valuation functions that we have so far. It could be arbitrary. Yes.
What does it mean to be proportional?
Proportionality just means that, let's say if there are n agents, then if I think of a division, then I should get at least 1/nth of the resource, right? I deserve 1/nth of the resource, because if I consider equality, that the resource is equally divided, 1/nth of my value of the resource. Yes.
How does agent 1 get preference 1 when he is dividing it equally?
So agent 1 has some preference of the cake, right? Let's say he likes the vanilla, he does not like the fruits. So he'll cut the cake such that one part contains some part of vanilla and the other part also contains some part of vanilla. So no matter which part he gets, he will get something from of vanilla.
Yeah, but like you told that in some cases agent 1 and agent 2 will get 1 as
Sure, agent 2 can get 1, but agent 1 will get exactly half in this case. Yeah, but there can exist allocations. If you run this protocol, then agent 1 will always get half of his value. But then there can be envy-free other divisions which in which they can get 1 value each. That was the point. Yeah. Okay. So if we have some understanding of this n equal to 2 envy-freeness and proportional division, let's see what we can do about n agents, right? We are going from 2 to n agents, and what we want is a proportional division of the cake. So this is a procedure that was again proposed in early 1960s. So what we do is we consider this interval 0, 1 again, and we move a knife from the left end point, and we keep moving the knife until an agent shouts, "Hey, stop! This point is now a point where I value this fraction at 1 by n of my value." Right? Whenever an agent shouts, we cut this piece and give it to that agent, remove that agent from the instance, and cut this cake. Right? Then what remains is this cut part of the cake, and we repeat this with the n minus 1 available agents. Do you agree that everyone will get a 1 nth of their value from this? No. Which agent will not get 1 nth of the value? But will he get less than 1 nth of the value or more than 1 nth of the value? It will always get more than 1 over n. Why? Because what we are doing is, if he valued any of the cut part of the cake at 1 by n, then he would have shouted before only. He would not have kept quiet.
For all the cuts, he must have valued them less than 1 by n.
Exactly.
So at the end, he must have been left with more than
With
1.
more than 1 by n. Do you agree? Yeah. So any agent who leave earlier always get exactly 1 by nth of this value because he shouted. His fault was that he shouted. But if he didn't raise his hand, if he stayed till the last, he would have gotten something more than 1 by n or exactly 1 by n. It could be anything. Okay. So I think we agree that this will give us a proportional division. But do you see it will also be envy-free or it will not be envy-free? Any comments on that? Who can envy here? Who can probably? The first agent. Look at the first agent. He shouted very early on, and then n minus 1 over nth of his cake was remaining, and then somebody might have gotten more than 1 over nth of his utility, right? The first agent who exited. So in generality, any agent who exits earlier might envy any agent who is exiting after him. Yeah.
But the thing is, when an agent is shouting, he is getting his like 1 over nth of.
Yes.
Right.
Yes.
So why would he envy? Because he has his bare minimum.
He has, so envy does not rely on having bare minimum. I could have anything. I could have 0. But if everyone also has 0, then I'm also envy free. Right? You don't allocate the cake. Nobody gets the cake. I'm envy free. Because I always look at the person and envy. I don't look at the remaining cake, and I don't envy the cake. I envy the person.
So some other person who has 1/n of its utility,
Yeah.
but more than 1/n of
My utility. Yeah. That agent will envy me. Right? So this suggests that for n agents, proportionality does not imply envy freeness.
But here, why will anybody shout?
This is the procedure, right? This is the procedure.
So they have to abide by the rules.
Yeah, yeah. So actually this is not the shout. So now the Robertson-Webb query model will come into picture. It's not like people were sitting in the room. So how do we model it computationally, right? So we have this oracle which will give us the queries. Can we think how many queries will it require to find this proportional division? Right. The first query we ask is, okay, I'm moving my knife. What is the point where you get your 1/nth of the value? So this is kind of a cut query, right? We ask first cut query. We ask this query to every agent, to all the n agents. What is the point y where you get 1/nth of your value, right? For each of these, for all of the n agents, I have a value y. I pick the leftmost y point, right? So in general, how many queries will suffice to get a proportional division? Can we have a guess? Exactly. Exactly. So in the first round, I go to all n agents and ask what is your value y, In the second round, I ask all the n minus 1 agents, so on so forth, and yeah, so this will give me at most n square queries are enough to get into a proportional division of cake. That makes sense, right? Okay, so we agree that this might not, yes.
Sorry, this might be obvious, but if, I mean, this is in a continuous setting, right?
This will give you a continuous allocation, yes.
But in that particular case, don't you kind of have to ask people at every point? Of course, you can probably discretize that. So I guess I don't really follow how you only need n squared many queries when you essentially need to ask kind of at every point, right?
You don't ask at every point, so we are only asking the cut queries. I'll give you the point, the initial point x, and I'll ask, give me your point y where you have a value of 1 by n. I won't ask it at every point, but I'll ask you, give me a point where you value it at 1 by n, I'll cut it at that point.
I see.
Right? Yes.
Can this create situations where there will be some agent I where their valuation is less than 1 by n?
Can it happen?
I feel like maybe
So if that happens, that agent will not output that y, right? So we are asking the query in the manner that, do you value it at 1 by n, then output me that y, and I'll cut it at that y. Why will it be less than 1 over
for
n?
the last agent.
For the last agent, he did not he did not value any of the earlier points y at 1 by n. Right?
How is it guaranteed that for the n minus 1 agent,
Yes.
that it is within the 0 to 1 range? Because aren't we it's not exact, we're not summating 1 by n, 1 by n, but 1 by n utility we're adding up, right?
Yes.
So,
So yeah, so I might not get exact, so if you mark 1 by n uniform divisions of the cake, I might not get that 1 by n, but whatever I get, I value it at 1 by nth of the utility.
no, I mean, like, how do you know that you can fit all that in the 0 to 1 interval?
This is by a simple pigeonhole, I guess.
There will be intersecting sections of different utilities.
That can happen. All kind of intersections in the utilities can happen, but every agent will get a utility of at least 1 by n. That is the point. Okay? And not 1 by n uniform distributions of the cake, 1 by n of the utility of the cake.
So are ties broken arbitrarily? So if two people are
The ties can be broken arbitrarily, yes, for sure.
So suppose there's like 3 agents.
Yeah.
And the first agent shouts at like almost like 90% of the cake. And then
Sure.
yeah, the first agent leaves with 90%.
Yeah, so then none of the agents valued that 90% of the cake at 1 by n. All the value lies in the last 10% of the cake. Maybe that has a chocolate or something, so all the value lies on that part. That's it. Yeah. Okay, so this procedure gives you a proportional allocation, but it is not NV-free. We want to design an NV-free procedure. We are willing to get rid of this assumption, the continuity assumption. That's fine if agents get pieces of crumbs of cake. If not a continuous fraction, we are fine with that. But even without that assumption, can you give me an NV-free division? This is one of the most important cake division open question. Not open question, we know the existence, but for at least for continuity requirement, we don't know a finite protocol. Okay, so let me give you a simple algorithm for 3 agents. This also has a flavor of cutting and choosing. So you remember the cut and choose protocol for 2 agents, right? Here we have 3 agents. Agent 1 will come and cut the interval into 3 equal parts. So he values all the 3 parts equally. Agent 2 will be asked to choose which is the part that you value the most, right? Suppose he says, okay, x1 is the part that I value the most. Then he'll be asked, okay, cut x1 to such a point such that you value the remaining part, this x1 minus x part, and x2 equally, right? So what agent 2 is doing is creating two equal partitions from x1 and x2, right? So this is what we call trimming of the cake. Right now we have not done any allocation. We have just agent 1 has divided into 3 equal parts. Agent 2 has divided into 2 equal parts, x1 minus x prime and x2. Now what happens is, let's ignore the trimming for now and look at this part. Agent 3 is now asked to choose any of these parts, right? Let's say he chooses x2, right? can you complete it into an envy-free allocation of only this part without the trimmings? Can we do that?
I have a question.
Yeah.
So why is agent 2 only trimming x1, x2 part?
So agent 2 said that, okay, out of these three pieces, I valued x1 as my best piece, right? I valued x1 the most. So now he is asked to, okay, fine, you like x1 the best, that's fine. You cut x1 and throw away the trimmings for now, and such that you value this part and this part equally, right? This is the protocol that we are following, and I just want to ensure that if you do this, it will give you an envy-free allocation of this part of the cake. Do you all agree? Agent 3 would be envy-free because he gets to choose between the three parts. That is fine.
X2 is having the second highest value for agent 2, right?
For
X2 is that piece that is having the
second highest value, yes, yes.
So if agent 2 valued x2 more, on which side will I trim?
It's fine. You can trim in between also. You can create fragments of the cake. That's fine. We are not looking for continuity.
Okay, so if okay.
Yeah. You can trim away any part you like in between at the end. Doesn't matter. But just that the two parts that remain, that you value that you value most, are equally valued by you. Right. So now, if agent 3 picks any part, he is not envy free. What agent 2 does is he valued two parts equally. So there is one part that remains. He can choose that part. Right. So he does not envy agent 3 for now. Agent 1 gets one of the parts, right? One of the non-trimmed parts. So he is also envy free. Right.
Always gets x3.
Sorry?
In this case, he
In this case he gets x3, yeah. Right. So at least for this division, this part of the cake, we have an envy free division, right? Now we have to deal with the trimmings. What do we do about the trimmings? Any suggestions?
So basically x1 was the part that agent 2 liked the most.
Yes.
Okay. Yeah.
Yes.
Repeat the procedure on the trimmings.
Repeat the procedure on the trimmings, that is right. But we will not follow the same ordering of these agents. Now we want to cut the trimmings. What we'll do is, okay, so this is the envy-free allocation of the non-trimmed part. Okay, so let's focus on trimmings now. We'll ask agent 3, who chose first, who did not participate in cutting the cake. You come and cut the trimming into 3 equal parts. Then agent 2 comes and pick his favorite trimming. Agent 2 comes and pick the remaining favorite trimming, and whatever last goes to agent 3. Right? Can you see that this division of trimmings is envy free? Sorry?
You're repeating the process of suppose you're trimming
No, not right now.
So agent 2 gets to go first, right? So agent 1 may envy agent.
Okay.
But did agent 1
Agent 1 actually has already gotten his entire piece x3, right? So what will plan to do is to merge the division of these trimmings into these trimmings, right? So agent 2 already got a 1/3 value of his cake, right? And he is getting some extra trimmings on the top of it. Does that make sense? Agent 2 is getting a trimming of it. So you see, x1 was the trimmed piece, and agent 1 liked this entire piece equally as he values x3. So he does not envy this entire piece even if you add all the trimmings to it. What is agent 2 getting? Agent 2 is getting the trimmed piece plus some part of this trimming. So we are sure that agent 1 values this entire part at most the value that he values it at, the value he derives from his fraction x3, right? So the subtlety here is that we ask the agent to choose who trimmed first, right? Whichever agent trimmed, we asked him to choose, so that this agent get a subset of this part, and then agent 1 does not envy this guy. That is the protocol, right? Okay, so for n equal to 3, we yes.
Just repeat the trimming piece, just like just the procedure from the beginning.
Okay, sure. Okay, so what is happening is, you understand the envy-free division of this part of the cake at least? The non-trimmed.
Yeah.
Okay. Let's look at the trimmings. So agent 3 cuts it. So he will never be envious, whichever piece of the trimmed cake he gets. Agent 2 picks So he will never be envious of anyone, at least for the trimmed part. Agent 1 might envy agent 2 because he went first, but now when you put it all together, right, agent 1 already valued, if you look in this fraction, agent 1 valued the entire x1 along with the trimmings equal to his division that he has already gotten. So he will never envy agent 2 who is getting something more from the trimmings prior to that guy. Yeah.
After the first iteration, in the
Yes.
second iteration when we're dealing with only the trimming,
Yes.
can't we like remove agent 1 from this process? Because agent 1 is already satisfied with this x3, right? So he won't be envious.
What could happen is agent 3 is getting some part of the trimming and is also getting, what is agent 3 getting here? X2. He is getting x2 plus something more. Now agent 1 can be envious, so we want to make sure that agent 1 gets something, and agent 1 picks before agent 3 here, so he will not envy agent 3.
But you asked agent 2 to, pick two parts and trim such that both of them have equal.
Yeah.
So what about the third part? The agent 2 might be envious that somebody will get the third part as well and some trimming as well.
So agent 2 right now does not envy anyone because he get his best valued part. You agree?
So among two, is that?
Yeah, among x1 minus x prime and x2, both he values equally, and he does not envy anyone right now.
So
Now what is
x3?
x3 is his least valued part of the cake. He values x2 more than x3. Yeah. Okay, so we see that even for 3 agents we had to do a lot of work, a lot of case analysis and a lot of trimmings. But so we know that envy-free cake division exists for 3 agents, fine. What Grams and Taylor showed in 1995, after approximately 35 years after this result, is that an envy-free cake division exists for n agents, and there is a finite but unbounded procedure to compute that. Unbounded procedure, I mean that you cannot have in the Robertson-Webb model, you cannot give a bound on the number of queries that, okay, given these n to the n many queries, you can find an envy-free division. You don't have such a bound. It can be, the number of queries can be arbitrarily large, but an envy-free division exists. Okay, so for a long time, this question was open, whether there exists a bounded procedure to find, so that if it is bounded, then we can compute it efficiently, right? Otherwise, what good is all this existence part doing to us if we cannot compute it? Okay, so then recently, so in many papers, in many recent papers, it was stated as a crucial open problem in cake division setting, that can you give us a bounded envy-free protocol, because we know it exists, we just don't know how to find it. So after many decades of research, now we know that there is a bounded finite protocol, but what is the bound on the number of queries? It is n to the n to the n towers of n. It is exponential to the exponential to the exponential. But the good part it is we know that it is bounded at least. And the algorithm uses some nuanced techniques. The thing that we saw for n equal to 3 agents, one agent is coming to cut, and then there are trimmings, and then there's somebody else's. So it uses this kind of an argument as a core protocol and develop more nuances to it, add more nuances to it, and then they reach at this point that at most with these many queries you can find an envy-free division for n agents. Fine. There was a paper in 2009 that said that, okay, if you want an envy-free division, you will have to do at least n square many queries. This is a lower bound. And now we have an upper bound, and this gap remains wide open as of today as well. We don't know if we can narrow this gap, and maybe we can find in polynomial many number of queries if we can get a complete envy-free division. But if you want to sacrifice some fraction of the cake, the same paper talked that let's not allocate some fraction of the cake, then you can guarantee yourself an envy-free division in polynomial many queries. So given that you are ready to not allocate some part of the cake, you can reduce the exponential dependence on n to polynomial dependence, but that asks you to unallocate some part of the cake.
But then you can do the reallocation of that part.
That does not work. That part has to, if you do that, if you have to go into the reallocation of the trimming piece, then the number of queries rise to this towers of n.
You can have some like error margin, right? Okay,
Yes, yes, yes. So that is another area. So, okay. So this is all about fragmented cake division, right? Because you're doing the trimmings, giving agent trimming. So the cake is entirely fragmented. The next question is, can you have continuous divisions of cake so that every agent gets a chunk, not fractions? What we know in that context is such an NV-free division exists, but there cannot be any finite protocol for that. Right? So the requirement of continuity is a very subtle point, and so the research directions that have opened up after that is, you cannot give me NV freeness, fine, can you give me approximate NV freeness, that I envy this agent but my NV is bounded up to this margin, right? So those kind of questions are still going on, and there are breakthroughs in those directions.
So
Okay.
for
Yes.
you mentioned something about the Robertson model.
Yes.
What is that?
So Robertson web model is how do you elicit these preferences of the agents over a continuous interval. You cannot ask every subinterval to you cannot go to an agent and ask how do you value every subinterval. There are infinitely many of them, right? So you resort to an oracle kind of access.
Oh, okay.
So
the
yeah,
Oracle model is
where you have two kind of queries: the evaluate query and the cut query. Evaluate just asks you what is the value that you give to this subinterval, and cut is where do you cut the cake so that you derive this much value out of it. These two queries, and you can model all these n equal to 3 protocols that I mentioned into that Robertson web model, and get a polynomial time bounded queries.
Excuse me.
Yeah.
I just have like a small clarification for the first decision procedure that you outlined with the agent calling when to cut. So the points that were made was like the ties were resolved arbitrarily, and
Yes.
the people who call first will have NV. But how
Yes.
about the case that suppose there are like two agents?
Yes.
And there's a tie. Both of them want value at 90%. And
Both of them want a value of 90%.
like they both call at a time.
Okay.
And when they
So for two agents, we have the simple cut and choose protocol, right? You don't need this moving knife procedure at all. One agent can cut into two parts and the other can choose. So for two agents, it's very simple.
right. But what I was thinking is in that case when we do that splitting, the person, like the agent who gets called first will not have NV. Right?
The agent who bids first has a condition that you will shout when you reach one half of your value, right? You cannot get more than that value, right? Whatever value we have fed into the algorithm, because you'll shout only when you get exactly that much, and now you have ensured that you cannot get more than that if you shout, right? And the agents are truthful. If a point arrives where the value, they will shout. So we don't have strategy proof. We don't go into strategy, at least in this model. Yeah. Okay, so this was the story of divisible cake cutting. I want to spend some time setting up the notations for indivisible cake cutting also, because this field has gotten some attention in the last decade, last couple of decades, 2000 onwards. And what is interesting here is we talked about so much NV-free exists in cake cutting and how to find it. What is interesting in the case of indivisible setting is NV-freeness does not even exist. So we have one question less to worry about, right? It does not exist. There is no question of how to find it, and let's leave all that. Okay, so let me just set the model and see what kind of results we aspire for, at least in this setting. So here we have some items G1 to GM. Now forget about all the Robertson web query model, everything. This is an entirely new setting. So we have M goods and N agents, and we just want this kind of an allocation. One bundle X1, X2, X3, X4 for each of the 4 agents, and we want a complete allocation. All the goods must be in some of the bucket. Okay, so the valuations, how do we elicit the preferences here? It is just an M by N matrix. It is easier than the continuous counterpart. Every agent just give a number. Okay, I value A1 at G1 at 5, G2 at 10, so on and so forth. So this gives you an M by N matrix. And we deal with additive valuations for now. What are additive valuations? The value of a bundle is just the sum of the values of the goods inside that bundle. This is a simple additive valuation function, although in real world there could be many other kind of valuation functions that could arise. So let's say, for example, I derive a value if I get a pair of items together. If I get a pair of shoes together, right? There is no value for just one shoe for the left leg, right? So there can be functions which are non-additive and which appear in real world settings, but at least for the simplicity of elicitation, we'll restrict our attention to the additive setting for now. Okay, so we saw that envy freeness may not even exist. Why? Because you can have lesser number of goods than agents, then no matter how, so let's say there is only one valuable good that is to be allocated, whoever gets it, the other one will envy. There is no way you can get rid of this envy, right?
So in this case, it is not normalized.
We consider both settings, normalized and non-normalized.
So both parties. So if there are two parties, both parties must have the same total value.
That is fine, that is the assumption of normalization, but we deal with instances where you don't even worry about normalization and you can guarantee some sort of fairness in those aspects as well.
Proportionality in this case?
Proportional, the definition remains the same. You value, yeah, at least for the definition of proportionality, you want, even if there is no normalization, let's say agent I think I have it on the slides, but okay, sure. So whatever value I derive to the whole bundle, it could be different for different agents. If the instance is non-normalized, I should get 1 by n of it. Let's say I value the entire bundle at 100, you valued the entire bundle at 200. So my value will be, I should get 50 and you should get 100. That is the proportional value. Okay. Okay, so okay, the good thing is envy does not exist, so we don't need to compute it. One thing sorted. Also, deciding the existence, it may not exist, it cannot exist in some instances, but there can be instances where it exists. Can you bifurcate those two instances? Can you decide, okay, given this instance, there is an envy free, and given this instance, there is no envy free? This computation question is also hard to decide. This is a reduction from equitable coloring, a graph theoretic problem. And this is hard even when agents have binary valuations, when agents have like 0 and 1 valuations. Forget about large numbers, even with binary valuations, this question is hard. Okay, so what do we do in this setting? So there are some relaxations that are proposed not far back, but very recently. In 2011, Buddhist proposed this notion of envy freeness up to one item. Okay, you cannot guarantee envy free, fine. Can you do the following? You remove one item from the envied bundle, and now all the envy is gotten rid of. There is no envy in the system, given you can ignore one item from each of the envied bundles. Right? This is the definition of EF1. A stronger variant, a stronger approximation to envy freeness is EFX, where no matter which item you remove, you could remove any, even the least valued item from the envied bundle, and your envy will go away. Right? Okay, so we can see it through an example. There are 3 items, 2 agents, identical valuations, and this is the allocation. Right? Agent 1 gets G1 and agent 2 gets G2 and G3. Can you say that this allocation is envy free? Envy free it is not, right? It is easy to see because A1 values this bundle at 3 but his own bundle at 1. But is it EF1? Why? Yeah, agent 1 can choose to hypothetically ignore G3 and now it is an envy free division. Right. Is it EFX? Why? Because if you remove the least valued good, then your envy does not go away, right? So EFX is a stronger variant and is kind of useful because your entire envy might be subject to the allocation of one highly valuable good, right? EF1 does not capture that kind of a scenario. It will say that, okay, just remove that highly valuable good. But then your entire envy is because of that good. Why would you hypothetically remove that? So EFX come to the rescue there and says, you remove any item, you remove even the least valuable item, then your envy will go away. So the correspondence between the notions is as follows. Every envy free allocation is indeed EFX and every EFX allocation is EF1 and not the converse. Okay, so good that we have defined all the approximations and stuff, but what about the computation and existence? Yes.
In EFX, we remove the least valued item.
Yes.
So least valued according to which agent?
Least valued according to the valuation of agent 1 who is envying agent 2, right? So if you look in the definition, it is I's perspective with which we are comparing, right? So your removal of good will happen from I's perspective. Yeah. Okay. So the results we know for EF1 are very positive, very encouraging, that EF1 will always exist. So, and this is a very strong result to say, right? We know that envy freeness may not exist even with one item, two agents, but then we are going ahead and say, no matter how many agents are there, how many items are there, you can always find an envy free allocation where you can remove at most one item and you will guarantee envy freeness. This is a very strong result to say, and it follows by a very simple algorithm. I'll come to that algorithm. But what we don't know is about the existence of EFX. Even beyond 3 agents, we do not know whether EFX allocations exist or do not exist. Right? Even the existence question is open. We don't know if it exists or it does not. So there has been a lot of work going on recently on the existence of EFX allocations. So people have looked at 2 agents. We know that if there are 2 agents, you can design protocols that can give you EFX allocations in reasonable amount of time. For 3 agents also, for 2 types of agents, by 2 types I just mean that if you look at your valuation matrix, there are only 2 kinds of rows. There are only 2 types of agents. Does that make sense? Okay. There also have been many domain restrictions that people come up. Okay, so EFX, we don't know the existence in general, but can you put a graph on agents and vertices and say that we look at NV only on the edges and vertices, or can you model the goods as edges of some graph and agents as vertices, and can you find an EFX allocation in the restricted settings? So there has been a lot of work going on where you restrict your valuation, where you restrict your input and try to see whether what happens with EFX existence. Okay, so given this is the story of the indivisible items, and I have I think 10 more minutes. I will go over this simple NV cycle elimination algorithm, which will guarantee you an EF1 allocation no matter how your valuations look like. They can be non-normalized, they can be non-additive, they can be monotone. Non-additive, by that I mean that not necessarily your valuation of a bundle is the sum of the items, it could be monotone. It just means that if you add something to your bundle, your valuation will only increase, it will not decrease. That is the monotone thing, right? So even with such monotone valuations, this simple algorithm will give you an EF1 allocation. So let's see how it works. So let's consider that these are the 5 agent vertices. We start with an arbitrary agent and allocate him any good, right? So this will increase his value, and what will happen is people might start envying him, right? Because right now nobody envies, with the empty allocation nobody envies anyone, that's fine. But the moment you allocate one item to one of the vertices, what could happen is people might start envying him. The moment they start envying, you just put these edges, these are the envy edges. What we are trying to create is an envy graph of an allocation, right? The moment I allocate something, the envy appears and I capture that envy with these edges. Okay, so what is happening is all these 4 agents are envious of this one agent. Fine. So what I do is I find an agent who nobody envies. We call it a source agent. Why source? Because there is no edge pointing towards this guy, right? So nobody is envying that guy. This is a source agent. So I can allocate some good to this guy. When I do that, the envy edges might change and people now might start envying him. And what could also happen is this guy might stop envying somebody else, right? All these scenarios can happen. Doesn't matter how they happen, but they are captured through these edges. Okay, so I keep giving items to sources, and once everyone has some item, let's say my envy graph looks like this, right? In this envy graph, again, what I'm trying to do is find an agent which does not have any incoming edge. Is there an agent here which does not have any incoming edge? G4, right? No incoming edge means that nobody envies him. He's a source in this graph. So you can go ahead and allocate something more. Right? So you allocate another item to this guy. Okay, so this might again change your envy graph. Your envy graph previously looked like this, but after allocating G6 it looks like this. Now is there a source in this graph? we can see that every vertex has an incoming edge, right? Okay, so what we do is, there is no source. What does that mean? Can you spot a cycle here? There are two cycles. So if there is no source, there is no vertex which does not have any incoming edge. Well, every vertex has an incoming edge, then you can surely find a cycle in this graph, right? So good. So you find an NV cycle, and what we do is we'll eliminate this cycle. How do we eliminate this cycle? What does the existence of this cycle mean? It means that this agent envies this agent, and this agent also envies this agent. If this happens, then just rotate these bundles, right? Exchange these bundles. So you will do that. Now neither this guy envies this and this guy envies this, right? The envy cycle is resolved. It is eliminated, right? Once it is eliminated, can you spot a source now? G1 again becomes a source, right? So you then continue this process, right? If you have a source, well and good, you allocate a good to the source. If you don't, then you will find an NV cycle, you eliminate that NV cycle, and then find a source, right? So in full generality, this is your simple NV cycle elimination algorithm that will run in polynomial time. Do you agree that all the goods will be allocated and this runs in polynomial time?
So do we only eliminate one cycle in first step, or all the cycles?
You can, in every step you can choose to eliminate one cycle, and that is enough. Or if there are more, you can, in the next step also you eliminate another cycle. In the next step you keep eliminating till you find a source, right? So I don't think I have time to go into the runtime of this algorithm, but I'll just mention that in each iteration, either you allocate a good or you eliminate a cycle. You do one of these two things, right? So either the number of goods is decreasing, or we can argue that the number of edges in this NV graph is decreasing, right? So this process is bound to terminate. It will terminate in polynomial time of in the size of the input, and it will. Can you see that it will give us an EF1 allocation? This is the main thing to argue, right? Why would we do all this if it does not guarantee a CF1? Okay, so what all we did in this algorithm? We just always allocated something to a source. Nobody envied the source. Now, after allocating an item to the source, if suppose there is an NV, we can always choose to hypothetically ignore the last added item, right? And that will that will guarantee that newly generated NV is now gotten rid of, right? So you start with a no allocation, right, which was initially NV free, and at every step you are creating an allocation that remains EF1 always, right? So that's the reason that when we allocate all the goods, the allocation remains EF1. Yes.
Is there any order in which the goods are allocated?
No. You can say that all goods are all agents derive positive value from the goods, and you can allocate any of them.
But would we
We can improve if we choose the best available good for that agent. That is fine, but it will again guarantee EF1 only. It will not have any improvements in the runtime or anything else. It will still be an EF1 allocation.
Can you go with that argument of EF1?
Yeah, so EF1 is when we are allocating a good, right? We are always allocating it to a source. Nobody envies the source. If new NV is generated, then you hypothetically remove that last added item to that source. You are back to your EF1 allocation.
So after the entire allocation is done,
Yes.
we have no cycles left.
Yeah.
And there is a source.
Yes.
So what do you do with the source now?
You allocate one of the unallocated items to that source.
Okay.
Right? Nobody envied the source. If somebody envies, you can choose to ignore the last added item. Right? And EF1 demands only that you must be able to remove at least one good. No matter which good, at least one good. Here we are removing the last added good. And the NV goes away. And in every step, the allocation we are building remains EF1. Right? Otherwise, we do not allocate anything to an agent who is envied already. Right? So that this will ensure that EF1, you achieve EF1 at the end of it. Yes?
Can we say something about the allocation being unique? Or
No, it can generate many EF1 allocations. Yes. It depends on which good what is the ordering on your goods. You can choose an arbitrary ordering and you can get a different allocation, but that is guaranteed to be EF1. Okay, I will stop here. And I'll just say that this is a very uh, this is a kind of an area of research which has gotten recent attention in last decade or two, the at least the indivisible setting, and a lot has been done and a lot remains to be done. So I talked only about proportionality and envy freeness as two fairness notions. There are many other fairness notions: equitability, MMS, egalitarian, utilitarian. There are many welfare notions where you don't only want fairness, because fairness is a more of an individualistic perspective. You also want to increase the collective welfare of the society, which is captured by the welfare measures, and then you want to look at the trade-offs. If you achieve fairness, what is the trade-off in the welfare that you have? If you want to insist on welfare, what is the trade-off in the fairness you have? So all these kind of combination of problems are a good research area in this domain of computational social choice that we discussed. So yeah, I'll stop here. Yes, one last question. Okay, sure.
Have time.
Yeah.
Like if you guys have time. So,
Yeah, go for it.
so I guess it's like a fairly general question.